The leather case arrived at the Tula arsenal in late November 1895, carried personally by a Belgian engineer whose reputation preceded him. Léon Nagant had spent 30 years building equipment for European militaries, but this presentation felt different. The Russian Commission had already adopted his rifle design 8 years earlier. Now they wanted a sidearm, and the specifications they'd provided were exacting, reliable, powerful enough for cavalry use, and manufacturable at scale in Russian facilities. Nagant opened the case to reveal a revolver that looked, at first glance, disappointingly conventional. The weapon lay against blue velvet, its frame a utilitarian black oxide finish without ornamentation. 7 chambers were visible in the cylinder, one more than the standard 6. The barrel measured precisely 4 inches, neither compact nor cumbersome. The grips were simple wood panels, designed for function rather than comfort. Colonel Andrei Golovin, chief of the arsenal's testing division, lifted the item and immediately noticed its weight distribution. Heavier than expected, balanced toward the frame rather than the barrel. "The cylinder mechanism," Golovin said, working the hammer back. "It moves." "Forward," Nagant confirmed. 3.5 millimeters. The cartridge case seats into the barrel-forcing cone when the action is cocked. This wasn't merely unusual. In 3 decades of military equipment evaluation, Golovin had never encountered a production revolver that intentionally moved its cylinder forward during operation. Every other design kept the cylinder fixed in position relative to the frame, accepting the small gap between cylinder and barrel as an unavoidable feature of revolver geometry. Energy escaped through that gap in every conventional design, reducing muzzle velocity and creating a visible flash at the cylinder-barrel junction. Nagant had brought 200 rounds of ammunition, each cartridge visibly different from standard military supplies. The projectile sat entirely within the brass case, invisible from the outside. The case mouth extended beyond the internal component in a slightly tapered cylinder that looked almost like a nozzle. "The case enters the barrel?" Golovin asked, examining a cartridge under the workshop's electric lamp. "Precisely. The seal is mechanical, not simply the result of chamber pressure." The other commission members had gathered around the workbench now, passing the revolver between them. Major Konstantin Petrov, the arsenal's chief machinist, opened the loading gate and rotated the cylinder manually. The mechanical resistance surprised him. The cylinder didn't spin freely, but moved with deliberate precision along carefully machined cam tracks. He could feel the engineering even through heavy winter gloves. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Léon Nagant had returned to his hotel room in Tula with neither confirmation nor rejection, only a polite promise that testing would begin in January. He sat at the writing desk, reviewing his cost calculations by lamplight. The gas seal mechanism required 18 additional machining operations compared to a conventional revolver. Each cylinder needed its cam tracks cut with precision, measuring in hundredths of a millimeter. The specialized ammunition would require retooling at the Russian cartridge factory in St. Petersburg. His brother Emil had warned him. The Russians want simple. They want what they can build in quantity. The Nagant brothers had built their reputation on understanding military requirements, translating field needs into manufacturable reality. Their rifle design had succeeded precisely because it accepted Russian manufacturing constraints rather than demanding Belgian precision. But the revolver was different. Léon had convinced himself that the performance gain would justify the complexity. The numbers told an uncomfortable story. A conventional revolver cost approximately 11 rubles to manufacture in Russian facilities. Nagant's sealed design would cost nearly 17 rubles per unit, mostly due to the precision machining and quality control requirements. For an organization planning to purchase thousands of sidearms, that difference compounded into substantial budgetary pressure. Yet Nagant kept returning to the ballistic measurements from his Belgian test facility. The gas seal increased muzzle velocity by 75 meters per second compared to an identical cartridge used in a conventional revolver. That translated directly to flatter trajectory and improved terminal performance at typical engagement distances. The question wasn't whether the seal worked, it demonstrably did. The question was whether Russian military doctrine valued that improvement enough to accept the additional cost and manufacturing complexity. Nagant had designed the mechanism to be as simple as the concept allowed. The cylinder rode on a crane that moved along two precision tracks in the frame. A camming surface on the hammer converted rotational motion into linear movement as the action cocked, pushing the cylinder forward at the exact moment the next chamber aligned with the barrel. Spring tension returned everything to its starting position when the hammer fell. No exotic materials, no revolutionary metallurgy, just conventional steel machined to exacting specifications. But exacting was the problem. Russian arsenals in 1895 possessed modern machine tools purchased from German and British manufacturers, operated by skilled machinists trained in the imperial technical schools. They could hold tolerances when necessary. The question was whether they would maintain those tolerances across thousands of units produced over decades. Léon had spent his career watching theoretical designs collide with production reality. Beautiful mechanisms failed when manufacturing precision degraded, when replacement parts were made by barely trained workers, or when field conditions revealed assumptions that had seemed reasonable in the workshop. The testing protocol began on a frozen morning in January 1896. The Tula arsenal maintained an underground firing range where temperature and humidity could be controlled regardless of weather. Colonel Golovin had assembled instrumentation borrowed from the Artillery Academy, chronographs for measuring muzzle velocity, precision scales for weighing cartridge components, and calipers accurate to 1/100th of a millimeter for checking dimensions after use. The fundamental mechanism revealed itself through systematic disassembly. When the hammer was pulled back in double action mode, a cam surface on the hammer's lower section engaged a curved track machined into the cylinder crane. As the hammer rotated backward, this camming action forced the crane, and therefore the entire cylinder, to slide forward along precision rails in the frame. Simultaneously, the hand advanced the cylinder to the next chamber. Both movements occurred smoothly in a single continuous motion. The timing was critical. The cylinder had to rotate to the correct alignment before moving forward, ensuring the next chamber was perfectly centered with the barrel bore. Then the forward movement occurred, pressing the extended cartridge case mouth into the barrel's forcing cone. A spring beneath the crane assembly provided resistance, storing energy during the forward stroke and returning the cylinder to its rearward position after use. Major Petrov measured the cylinder gap with precision feeler gauges. In the rest position, with the hammer down, a standard gap of approximately 0.15 millimeters existed between cylinder and barrel, normal for any revolver. But when he manually cocked the action and remeasured, the gap had closed completely. The tapered cartridge case mouth actually entered the barrel forcing cone, creating metal-to-metal contact across the entire circumference. The specialized ammunition made this seal possible. Unlike conventional cartridges, where the projectile protruded from the case mouth, Nagant's design kept the component entirely within the brass case. The case extended 7 millimeters beyond the internal projectile, forming a precisely tapered cylinder. When the loaded chamber moved forward, this extension entered the barrel, and the circumferential contact created the gas seal. Golovin conducted tests with both sealed and unsealed configurations. He modified several cartridges, trimming the case mouths flush with the projectiles to eliminate the sealing surface. Using these modified rounds through the Nagant revolver essentially created a conventional revolver for comparison purposes. The chronograph measurements confirmed Nagant's Belgian data. Sealed ammunition produced muzzle velocities averaging 275 meters per second, while unsealed ammunition from the same batch measured 225 meters per second. The difference was consistent across 50 rounds of each type. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The Arsenal's engineering staff identified 3 areas requiring revision before production approval. First, the trigger pull in double-action mode measured nearly 7 kilograms, substantially heavier than conventional revolvers. The mechanism was doing double mechanical work, both rotating and advancing the cylinder against spring resistance. Users accustomed to lighter triggers might struggle with accuracy under field conditions. Nagant returned to Tula in March with modified prototypes featuring redesigned cam geometry and reduced spring tension. The trigger pull decreased to approximately 5 kilograms, still heavy but more manageable. He couldn't reduce it further without compromising the reliability of the cylinder's return movement. The gas seal mechanism demanded that spring resistance. It was a fundamental trade-off inherent in the design. Second concern, the specialized ammunition. The St. Petersburg cartridge factory needed to retool their production lines to manufacture cases with the extended mouth. The seating depth required new loading dies. Quality control would be critical. If the case mouth wasn't perfectly concentric, it wouldn't seal properly in the barrel forcing cone. The factory superintendent estimated a 6-month transition period and recommended building substantial inventory before deploying the items to field units. Third issue proved most contentious: field maintenance. The cylinder crane mechanism required periodic lubrication and cleaning to prevent binding, particularly in dusty or muddy conditions. The cam tracks would accumulate debris that could interfere with smooth forward movement. Personnel would need specific training on disassembly and maintenance procedures beyond what conventional revolvers required. Major Petrov supervised durability testing through the spring. Each prototype was used for 3,000 rounds under various conditions, clean and lubricated, deliberately fouled with mud and sand, exposed to temperature extremes, and submerged in water, then used immediately. The mechanism proved remarkably resilient. Even when the cam tracks were packed with dried mud, the cylinder still moved forward under hammer force, though the action became noticeably stiffer. Wear patterns emerged after extended use. The cam surfaces showed polishing where metal contacted metal during thousands of operations. The precision rails supporting the cylinder crane developed slight grooves where the crane slid back and forth. None of this affected functionality, but it raised questions about long-term dimensional stability. Would the gas seal remain effective after 10,000 rounds? 20,000? Nagant addressed this concern by specifying hardened steel for all cam surfaces and rails. The hardening process added manufacturing cost, but ensured the critical dimensions would remain stable through the item's service life. He calculated that proper material selection and heat treatment would maintain seal effectiveness for at least 50,000 rounds, well beyond the expected service life for a military sidearm. 27 years after the Nagant M1895 entered Russian service, an engineer named Hiram Percy Maxim was developing sound suppression devices for hardware in his Connecticut workshop. Maxim's suppressors worked by allowing propellant gases to expand into a series of chambers, reducing their pressure and temperature before release into the atmosphere. The technology showed promise for long-range equipment and automatic devices, but conventional wisdom held that revolvers couldn't be effectively suppressed. The cylinder gap allowed gases to escape laterally, creating noise that bypassed any barrel-mounted device. Then someone at Maxim's facility tested a Nagant M1895 that had been acquired during various European conflicts and imported as a curiosity. The gas seal mechanism that Léon Nagant had designed to increase efficiency created an unexpected secondary effect. It made the revolver function mechanically like a sealed chamber system. When fitted with a suppressor, the Nagant produced sound levels comparable to suppressed semi-automatic tools, something no other revolver could achieve. This revelation occurred decades after Léon Nagant's passing in 1900. He never witnessed this application of his design, never imagined that the seal mechanism would prove valuable beyond its ballistic performance benefits. The gas seal had been engineered solely to capture wasted energy, to convert propellant gases that would otherwise escape into useful work. The suppression capability was accidental genius, a second-order effect that couldn't have been predicted in 1895 because suppressor technology didn't meaningfully exist yet. The Soviet armories that continued manufacturing Nagant revolvers into the 1950s began producing specialized variants specifically designed for suppressed operation. These versions featured slightly longer barrels to accommodate threaded mounts and were issued to reconnaissance units and security forces. The mechanism that Colonel Golovin had examined in Tula Arsenal 50 years earlier proved adaptable to requirements its inventor never anticipated. But the deeper engineering lesson wasn't about suppressors. It was about what happens when a designer refuses to accept conventional limitations. Every manufacturer since Samuel Colt had known about the cylinder gap. They'd measured the energy loss, calculated the velocity reduction, and concluded that the gap was an inevitable consequence of revolver geometry. Léon Nagant approached the same problem and asked a different question. Not how do we minimize the gap, but how do we eliminate it entirely? The answer required reimagining the fundamental mechanics. Instead of keeping the cylinder stationary and accepting the gap, Nagant made the cylinder mobile, creating a dynamic seal at the moment of use. This violated conventional design assumptions about how these tools should operate, but it worked precisely because Nagant ignored what everyone else accepted as impossible. The Nagant M1895 remained in production for nearly 60 years, manufactured in quantities exceeding 2 million units. Russian and Soviet arsenals produced the item from 1895 until 1954, an extraordinary manufacturing run that spanned the Russo-Japanese conflict, World War I, the Russian Revolution, World War II, and into the early Cold War period. No other revolver design in history achieved such sustained production across so many decades of technical and political change. The item's longevity revealed something important about engineering that transcends any individual mechanism. Nagant's gas seal was mechanically clever, but mechanical cleverness alone doesn't ensure adoption or sustained production. The design succeeded because it balanced innovation with manufacturability, achieving measurable performance improvements while remaining compatible with existing industrial infrastructure. Russian arsenals could build the Nagant M1895 with their available machine tools and trained workforce. The specialized ammunition required retooling, but not revolutionary new manufacturing processes. This balance becomes visible when comparing the Nagant to other innovative designs that failed commercially, despite superior engineering. Dozens of concepts from the same era offered theoretical advantages: more rounds, faster reloading, lighter weight, more powerful cartridges, but demanded manufacturing capabilities or supply chains that didn't exist. They were correct solutions to the wrong constraints. Nagant understood his constraints and designed within them, accepting the heavy trigger pull and manufacturing complexity because these costs were actually payable by his client. The gas seal mechanism itself became a historical footnote rather than a revolutionary innovation. No major military subsequently adopted the concept for standard use. Modern designers acknowledge its technical achievement while choosing conventional cylinder gaps for their own projects. The manufacturing complexity and ammunition specialization that Nagant accepted in 1895 became even less attractive as semi-automatic technology matured. Why build a mechanically complex revolver when a simpler semi-automatic could achieve comparable or better performance? Yet the Nagant M1895 endures in engineering education precisely because it represents a specific type of problem-solving that remains valuable. Léon Nagant identified a quantifiable inefficiency, developed a mechanism to address it, and implemented that mechanism within the constraints of contemporary manufacturing. He didn't create a device that changed the nature of conflict or defined an era. He created a device that worked exactly as intended, delivered measurable value to its users, and could be manufactured reliably at the required scale. That's engineering in its purest form, not the dramatic breakthrough that revolutionizes an industry, but the careful optimization that extracts slightly more performance from familiar materials and processes. The gas seal mechanism captured 15 to 20% more energy from each cartridge. That's not dramatic, but across millions of rounds used over decades of service, those small percentages accumulated into substantial value. Sometimes the most important engineering isn't the innovation that changes everything, it's the refinement that makes everything work slightly better. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching. Would you like me to translate another script or assist with further naturalization of this text?